Today we will discuss chapter number 1, real numbers. Real numbers, the subtopics are Euclid's decision lemma, the fundamental theorem of mathematics, and revisiting rational numbers and their decimal forms. So we start with the last topic, revisiting rational numbers and their decimal form. This is a little bit easy. Revisiting rational numbers and their decimal expansions. So you have already studied in 9th standard the rational numbers and decimal form also. So any rational number will be in the form how rational number, the general form of a rational number will be
E by Q.
E by Q form where
Q is
Not equal to 0.
yes, P and Q are
integers.
integers with the Q not equal to 0. So what do you mean by coprime numbers?
Only one factor.
Only one common factor. Suppose 1 is the only common factor between P and Q, then they are coprime numbers. For example, 3 and 5. 3 by 5. This is example for coprime number 3 and 5. Okay. So what happens if they are not coprime? Then we can reduce them, right? For example, 2 by 4. They are not coprime numbers. 2 and 4 are not coprime numbers because they have common factors 1 and 2. So we can reduce them 1 by 2. Then this is in the form P by Q, or P and Q are coprime numbers and Q not equal to 0. So in this topic we will discuss when we write the decimal form of a rational number, how will it look like. In some situation you have studied in 9th standard, the decimal form will terminate. For example, suppose 1 by 2, the decimal form. If 1 by 2 is a rational number, if you write the decimal form of 1 by 2, we'll get a 0.5. It is terminating. Terminating means there's an end. For some example, 1 by 3. So how is the decimal form? Can you tell the decimal form of 1 by 3? What's the decimal form?
3.333.
Yes, 0.333, etc. Okay. So we will discuss in this topic when a rational number terminates in decimal form and when it will not terminate. That's the only thing we study in this topic. What's the general form, general idea of a rational number which terminates in decimal form? That's what we discuss here. We start with some example questions. From the examples, we'll make some conclusions. Okay, so I think we can start with a very simple question. 0.25. 0.25. This is a decimal number which terminates. What will be its rational form? We know a decimal number.
1 by 4.
1 by 4.
1 by 4. 1 by 4 is the decimal form. So here there is another chance. Another chance to convert this. This is the short form. That's okay. That's okay.
2 by 8.
2 by 8.
2 by 8. That is also fine. Whenever you get a rational number, suppose 0.34. First, how will you convert this?
34 divided by
100. So this is how we think first. So 0.25 was an exception, very easy decimal form. We can directly find the simple form. Usually when we get a decimal form, when we get a question to convert to fraction form, we convert the decimal number into a fraction having powers of 10 in the denominator. Okay. So here also if you write like so you can write a 0.25 as 25 by 100. Then we can reduce to 1 by 4. So in other terms, you can write 25 by 10 square, powers of 10. 100 is 10 square. Okay? And there's another chance to reduce this. So we can remove the common factors. So 25 we can write as 5 square. And 10 square we can write it 10 2 into 5. 2 into 5. Okay, and 10 square you can write as 2 into 5 square. That is 10 square is 2 square into 5 square. We know this rule. AB all square is equal to A square into B square. So here we can write 10 square as 2 square into 5 square. We can cancel 5 square. So 1 by 2 square, that is 4. So you can reduce it. So when you get a terminating decimal number, when you write the fraction form, first you can write a fraction form with the denominator powers of 10. Sometimes maybe 100, sometimes 1000, sometimes 10,000. The denominator powers of 10. Then you can reduce to simple form. We will do some more examples and we will see some common pattern in their simpler form. So second example, suppose I take 0.375. So how we can write this in a fraction with the denominator powers of 10?
375 divided
10 raised to 3.
375 by
1000.
1000. We can write a 375 by 1000. So now we can reduce, we can cancel the common factors. So better you write the prime factorization and cancel the common factors. What's the prime factorization of 375? 375, what's the prime factorization of 375? Just try it.
5 cube into 3.
5 cube into 3, correct. You can write it 3 into 5 cube. So we start with a smaller number. Okay, 1000, how we can write?
5 cube and cube.
5 cube and 3 cube, right? So 1000 you can write as 2 cube into 5 cube. 2 cube into 5 cube. What is 2 cube into 5 cube? 2 cube into 5 cube will be 2 into 5 or cube. That is 10 cube, that is 1000. So why we split like this? Because in the numerator there is 5 cubes, so we can cancel it. Okay, or the 1000 in prime factorization we can write like this. So we can cancel 5 cubes. So what will be the balance? 3 by
8.
3 by 2. I think this is enough. 3 by 2 to get some general idea. This is enough. Okay. The previous example also 1 by 4. To make some generalization, better you stop here. The previous step. I need to come to the last step. Then we can make some general idea easily. Okay. The next example, one more example, 0.104. So first we write with the denominator power of 10. How we can write?
104 by
104 by
1000.
Denominator 1000, right? So how we can reduce this? What's the prime factorization of 104? Just try it.
2 cube into 30.
2 cube into 30, that's correct. 2 cube into 13 is the prime factorization of 104. What was the prime factorization of 1000?
2
2 cube into 5 cube.
2 cube into 5 cube. So here the common factors we can cancel. 2 cube into 2 cube. So balance will be 13 by 5 cube. Now one more we can do, last one. 0.0875. So I shall write the prime factorization of the numerator. Numerator will be 875 by 1000, not 10,000, because 4 is 10,000. So 875, the prime factorization is 7 into 5 cube is 800. 5 cube is 125. 7 into 125 is 875. Divided by 10, 10,000, how we can write?
4 into 5 raised to 4.
2 raised to 4 into
5 raised to 4.
5 raised to 4. So here 5 cube is common, so better you split the denominator like this. 5 cube divided by 2 raised to 4 into 5 raised to 4. You can also write 5 raised to 3 into 5 raised to 1. Why? There's a rule. A raised to n into a raised to m is equal to a raised to n plus m. So we can split, we can write 5 raised to 4 as 5 raised to 3 into 5 raised to 1. Why we write like this? Because we want to cancel 5 cube. So we can cancel 5 cube. So we get like this. 7 by 2 raised to 4 into 5. 2 raised to 4 into 5. So we got some of the examples. What we discussed is terminating decimal numbers. Some of the terminating decimal numbers we have chosen example. And we find their rational form. What we got here we can analyze. First one is 1 by 2 square, next one is 3 by 2 cube, and third one is 13 by 5 cube, and last one is 7 divided by 2 raised to 4 into 5. Okay, So here you can see some specialty in the denominator. So in the first one, only 2 square, 2, powers of 2. Second one, only powers of 2. Third one, powers of 5. In the fourth one, a combination of powers of 2 and 5. So if you do more examples, if you do more and more example, you can see in the denominator of those decimal number they are terminating, when we convert to rational form, their denominator will only contain powers of 2 and powers of 5. Only if they are terminating. If the decimal number is terminating, when we write their fraction form, when we simplify them, when we convert them into a fraction of co-prime numbers, numerator and denominator, we can see their denominators contains only powers of 2 and powers of 5. Okay, that's the idea of rational numbers, their decimal forms terminates. Okay, in the rational form, the denominator will contain prime factorization powers of 2 and powers of 5 only. Sometimes only powers of 2, sometimes only powers of 5, sometimes a combination or product of powers of 2 and powers of 5. The first example, 2 square, we can write 2 square into 5 raised to 0, that's fine. 5 raised to 0 is 1. And in the third example, you can write it denominator as 5 cube into 2 raised to 0. 2 raised to 0 is 1. So in general, we can say if p by q is a rational number whose decimal form terminates, then q can be written as in prime factorization. In prime factorization, we can write q as 2 raised to some natural number into 5 raised to some natural number. And then there are some integers, right? Positive integers. So this is the idea if the decimal form of a rational number terminates. In the prime factorization of the denominator, if suppose for example 2 square into 5 cube into 3 or something, then that's the opposite case. We have a special theorem for this. We'll study today itself. Anyhow, in this example, since the denominator is not in the form 2 raised to n into 5 raised to m, the decimal form will not be terminating. But here you have to ensure that the denominator is taken after removing all the common factors with the numerator. There are two methods. You can cancel the common factors after the prime factorization or before the prime factorization. Anyhow, the final denominator should be taken after removing all the common factors with the numerator. Just look at an example. Suppose the given fraction is 3 by 6. 3 by 6. So here the denominator is 6. The prime factorization of 6 is 2 into 3. That is not in the form 2 raised to n into 5 raised to m. But we know that 3 by 6 is 0.5 because 3 by 6 is equivalent to 1 by 2. Okay, so this is happened because we have taken 6, the denominator, not after removing all the common factors with the numerator. So that thing you want to ensure the denominator is taken after removing all the common factors with the numerator. That is, the numerator and denominator are co-primes. To generalization, I put 5 raised to 0. Need not be, okay, only for generalization I put 5 raised to 0. So simply 2 square means that's also in the form product of powers of 2 and powers of 5, where exponent of the 5 is 0. So let's discuss some more example. Okay, look here, 3 of them we discussed already. Look this example, 23.3408. So you can write fraction form like this, 2,33,408 divided by 10 raised to 4 here. Okay, here the point comes 4 placed to left. So denominator you can take as 10,000. So look here, the prime factorization of the numerator is like this. And here you can
5 raised to 4.
yes, that okay, this is not prime factorization. This is after cancelling the common factor. If you write the prime factorization of this numerator, it will be like 2 raised to 6 into. If you write the prime factorization of this numerator, it will be 2 raised to 6 into this. And the denominator, you can write it 10 raised to 4, you can write it 10 raised to 4, you can write it 2 raised to 4 into 5 raised to 4. There you can cancel 2 raised to 4 and 2 raised to 4. The balance will be 2 raised to 2 square, right? That's why 2 square comes here. The 2 raised to 4 is cancelled with the denominator. That's why the denominator only having 5 raised to 4. 2 raised to 4 is cancelled as a common factor. Okay, so this is the idea. Why only 2 and 5? Did you think so? Why only 2 and 5? Okay, the idea, yes, the idea is, in a simple way we can say, if a decimal form terminates, then those numbers we can express as a fraction with the denominator powers of 10. The fraction having decimal form terminating, we can express in the form of a rational number with the denominator powers of 10. So we are simplifying those fractions. In some of the case, if numerator having some common factor with the denominator, we can simplify them. We'll reach only in the form 2 raised to n into 5 raised to m. Why? This is because the prime factors of powers of 10. Which are the prime factors of powers of 10? Which are the prime factors of 10? 2 and 5. Which are the prime factors of 100? I say 2 and 5 only the prime factors of 100. Which are the prime factors of 1000?
2 and 5.
2 and 5 only. So for any power of 10, whether 100 or 1000 or 10,000 or 1 lakh or 10 lakh, the prime factors of powers of 10 are only 2 and 5. Okay, so that is why only 2 and 5 comes in the denominator in the simplest form of the given rational number. Okay, so there are some reverse questions. So when we discuss the reverse question, I hope it will be more clear. Okay, so what we discuss now, we can form a theorem like this theorem. Let x be a rational number whose decimal terminates. Then x can be expressed in the form p by q, where p and q are coprime numbers, and the prime factorization of q is of the form 2 raised to n into 5 raised to n. This is what we discussed here, so we make a theorem like this. X is a rational number whose decimal expansion terminates at a point. Okay, then we can write x as in the form p by q, where p and q are coprime numbers with q denominator in its prime factorization having in the form 2 raised to n into 5 raised to n. No other numbers, no other powers, only 2 and 5 power, no other prime numbers comes in the prime factorization. Okay, this is the thing. Now we just think the reverse. So if a number is of the form p by q, a rational number in the form p by q, a denominator can be written in the form 2 raised to n into 5 raised to m, is the decimal form terminates. Well, the previous theorem we discussed just before this theorem in the screen, we discussed if decimal form terminates, then we can write in the form p by q, where q is of the form 2 raised to n into 5 raised to m. Next we start with this. If q can be written in the form 2 raised to n into 5 raised to m, does the decimal expansion terminates? Actually both are same. So simply try some example. Suppose, okay, so I'll show some example in the textbook, that's enough. Very simple question. Okay, look here, 3 by 8, the denominator, like we can prime factorization like this, 3 by 2 cube. 3 by 2 cube. So 3 by 8 can be written as 3 by 2 cube. Now by suitable adjustment, we can take equal fraction like this, 3 into 5 cube by 2 cube into 5 cube. Okay, so why we do like this? Why we do like this? Yeah, to form the decimal number. There are some questions in the exercise. to find the decimal form of the given rational numbers. To find the decimal form of given rational number. So the best method is you make the denominator power of 10. Make the denominator power of 10. Then you can write the decimal form very easily. Okay, so the given question is 3 by 8. So you may expect some questions like this. Write the decimal form of 3 by 8. So the idea is 3 by 2 cube. You can prime factorization. This 8, you will get it 2 cube. Then to reach in power of 10, the idea is you want to multiply 2 cube with 2 cube with 5 cube. So it will become 10 cube. Okay. So to balance this 5 cube, you want to multiply the numerator also with 5 cube. So 3 into 5 cube by 2 cube into 5 cube, we will get a 375 by 10 cube. Then you can write the decimal form very simply. Dividing with 1000 means putting a point 3 place to left. 3 place to left. So 5, 7, 3. Here we want to put the point. Okay. So here we need only this. So 3 by 8. 3 by 8 is a rational number whose denominator is 8. 8 can be written in the form 2 cube. Or in other words, we can say 2 raised to n into 5 raised to m. In this case, in the case of 8 here, the 5 raised to m is 0. Okay. Then we got the decimal form terminates.
Does it needed to be n is equal to m?
Yeah, some situation. Some, for example, 19 by 100. 19 by 100. If you do the prime factorization 19, 2 square into 5 square only you can write. The 100 you can write it 2 square into 5 square. In some situation, the n and m can be equal. Okay. So come to these examples again. So 3 by 8 is a rational number whose denominator 8 can be written in the form 2 raised to n into 5 raised to n. So 8 can be written in 2 raised to 3 into 5 raised to 0 is there. So we can say the denominator q, here q is 8, can be written in the form 2 raised to n into 5 raised to n. Then the decimal form of this 3 by 8, this rational number is terminating. Now we just take another example, 13 by 120 into 125. 125 is the denominator q, and it can be expressed in the form 5 cube. 5 cube is 125, we know. 5 into 5 into 5 is 125. That means the denominator of this rational number 13 by 125 can be expressed in the form 2 raised to n into 5 raised to n, where n is 0, right? Only m is 3 and n is 0 in this case. Anyway, we can say denominator of this rational number can be expressed in the form 2 raised to n into 5 raised to m. And then the decimal form of this rational number is terminating. How? So to get equal fractions, we can multiply numerator and denominator with the same quantity. We know 1 by 2 is equal to 2 by 4 is equal to 3 by 6 is equal to, etc., etc. For any rational number, there are infinite number of equal fractions. So we convert the given fraction, the rational number in other terms, we can say a fraction. The fraction we can convert to another fraction with the denominator power of 10. So here already 5 cube there in the denominator. So to get denominator power of 10, you can multiply this denominator by 2 cube. So to balance the rational number or the fraction, we want to multiply the numerator also with the 2 cube. So 13 into 2 cube, we will get 104, and denominator it will become 10 cube. So then if you write the decimal form, denominator is 1000. So moving right to left to 3 place, you want to put the point, you get 0.104. So the decimal form terminates. So 2 examples we all discussed. And third one also, 80 is the denominator. 80 can be written in the form 2 raised to n into 5 raised to m. Then its decimal form also terminates. And 625 can be written in the form 5 raised to 4. That means that is also in the form 2 raised to n into 5 raised to m, and its decimal form also terminates. So from this example, we generalize. If a rational number p by q, where p and q are coprime, and q can be written in the form 2 raised to n into 5 raised to m, then its decimal form will terminate. Then the decimal form of this rational number will terminate. So 2 theorem. Now we just discussed just a reverse what we discussed just before. So clear my page. 2 theorems. So look here. The first theorem was, if the decimal form of a rational number is terminating, then that rational number can be taken in the form p by q, where p and q are co-prime, and q can be written in the form 2 raised to n into 5 raised to n. Okay, so here decimal number terminating implies, if the decimal form of given rational number terminating, then that implies the denominator q can be written in the form 2 raised to n into 5 raised to n. The second theorem, it is there in the second page, that is just a reverse. If a rational number p by q is of the form denominator in the form q is equal to 2 raised to n into 5 raised to n, then that implies the decimal form of that rational number terminates. That's the difference between these two theorems. So I shall show the second theorem in this place. Just reverse. Okay, here look. Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to n into 5 raised to n, where n and m are non-negative integers. Then x has a decimal expansion which terminates.
Correct.
Yes.
Powers same ആണോ?
Powers need not be same. N and m need not be same. N and m can be different non-negative integer. Maybe equal, maybe not equal. I repeat one last time. So if a number, rational number, has terminating decimal form, then that number can be written in the form p by q, where p and q are co-prime numbers, and q in prime factorization we can write in the form 2 raised to n into 5 raised to n. That's what discussed here. And just to reverse also, if p by q is a rational number with p and q are co-prime numbers, and q in prime factorization it is in the form 2 raised to n into 5 raised to m, then we can say the decimal form of this rational number will terminate. Okay. In the next video, we will discuss some more questions based on these theorems. If you like this video, please don't forget to press the like button and also share this video to your friends. If you haven't subscribed this channel, please subscribe this channel. I have uploaded more videos of class 10 CBSE students, so you can find out those videos from the links in the description of this video. So see you in the next video. Bye.